We're going to wrap up our forces unit here with talking about what I call multibody problems. That's not necessarily the technical name for it, but that's what I always say. So these are problems where we have multiple objects, right? So far we've really, except for maybe a few exceptions, we've really only dealt with situations where there's a single object. Now we're going to deal with situations where there are multiple objects. And there's really three key ideas, three key concepts that arise from these situations. The first is that the objects are all accelerating at the same rate if they're connected, okay? And that just makes sense when you think about it. If two objects are touching or somehow connected, the acceleration of one object has to be the acceleration of the other because they're moving together. So that's our first key concept. The second is the forces between the objects obey Newton's third law. So we're always going to have some force that is the force that connects the objects, that allows these objects to interact. Okay, we're not going to deal with problems with multiple objects that aren't interacting. These objects will be interacting, and that means that the forces between them will be equal and opposite. Okay, and that's going to play a really, really key role and make our life a lot easier. And the third concept, which is kind of going to be another way of approaching these problems, is that groups of objects can be treated as a single object. And this brings up the idea of a system. And this is something we're going to talk about a lot as we move forward into the next few units. We haven't really talked about it much, but the basic idea here is we can treat multiple objects as a single object. And it changes how we think about our situation a little bit, but our rules, our physics concepts, all the ideas we've been studying, they're all the same when we treat multiple objects as a single object, as a single system. And so we'll take a look at exactly how that applies with these multibody force problems. So when we're doing these problems, there's going to be a few key ideas that we're going to do almost every single time. And so here are some tips for solving these. First of all, we're going to start out treating the objects as separate objects. And we're going to do our F equals ma and our free body diagram for each of the objects. Okay, that's our first big idea. Second is we're going to use Newton's third law. That's going to be highly important in these problems, but use Newton's third law to link those equations, to bring them together, because we know that those forces that the objects exert on each other are always equal and opposite, and we can use that to help connect our equations. And the other thing, and I know I say this a lot, but it's extra important here, is be very, very careful with your signs. You really want to think about the direction of your force and your acceleration and make sure you're consistent with your signs. The one thing I would say with this, and you don't necessarily have to do this, but what I usually do is I make acceleration be positive, and we'll look at what that looks like as we go throughout this unit. But I think it's easiest to make the acceleration be positive always. And it's going to allow some things to cancel out nicely, as you'll see in the next few problems. So for this first problem, we have a train consists of 3 cars with masses shown below. An engine pulls them with 8,000 newtons of force. And so what we want to do is we want to think about what is the acceleration of these 3 cars, and then how much force is exerted by the third car on the second, and how much force is exerted by the second car on the first. So what I'm going to do is I'm going to start off drawing 3 free body diagrams for each of these objects. So on that 500 kilogram object, object 3, we're going to have a normal force from the track, we're going to have the force of gravity, and we're going to have this force pulling it. We see that there's a connection here between the 2 cars. And so I'm just going to call that the force of car 2 on car 3. Up next we have that middle car, and so that's going to have a normal force and a force of gravity as well. Now that middle car is being pulled by the connection between 1 and 2, so I'm going to say this is the force of 1 on 2. And we keep in mind that this connection between 2 and 3 still exists, and that affects both objects. So we also have a backward force here, and that's the force of 3 on 2. Lastly, we have that first car, the 700 kilogram. We have normal and the force of gravity on them as well. We have that forward pulling force from the engine, which is 8,000 newtons. And we have the connection between 1 and 2. Once again, just like 3 affected 2, 2 affects 1, and so we're going to have a backwards force here of 2 on 1. Now, I just want to point out here that right here we have a third law pair, 3 on 2 and 2 on 3. And right here we have another third law pair. We're going to keep that in mind as we're setting up an F equals ma for each one. These objects are all going to be accelerating to the right. That's the direction they're being pulled. And so I'm not actually even going to bother here with thinking about my y forces. They're really not going to come into play. You could set up your y equations for each, but it's just going to tell you that the normal force equals gravity, and you're going to see it's not really going to help you. So I'm just going to set my x equations for each. So for the first one, we have the force of 2 on 3. It's the only force we have, and that's going to be equal to 500 times a, the acceleration of object 3. So for object 2, my F equals ma, I'm going to have the force of 1 on 2 minus the force of 3 on 2. Okay, that's the sum of the forces, and that's going to be equal to 800a. Notice that I'm going to make my accelerations be the same variable because they represent the same thing. We talked about how these objects are moving together before. So if they're moving together, accelerating together, they have to have the same acceleration. So I can call it the same thing. For my last object, object 1, my F equals ma is going to be Fp minus the force of 2 on 1. That's equal to 700a. I know what the value for Fp is, but I'm going to leave it as a variable for now. So now we have 3 equations, and what we really want to do is be able to combine them to ultimately solve for our acceleration. So there's lots of ways of doing this, but I'm going to show you what I think is the most clever way of doing this. And it's actually going to give you a nice little check to see that you set up everything correctly. So here's how I'm going to combine them. I'm actually going to take our 3 equations, right, on object 3, on object 2, on object 1, and I'm going to add up those equations. So we're going to add all of these equations together. And what I'm going to see is when I add them on the left side, we have f of 2 on 3 minus f of 3 on 2. Well, they're the same value, so they're going to cancel out. We have f of 1 on 2 minus f of 2 on 1. Those are also going to cancel out, so that left side simply becomes fp. And it's going to be equal to 500a plus 800a plus 700a, or 2000a. And so I can plug in for FP, 8,000 equals 2,000a, and that means that my acceleration is just 4 meters per second squared when I divide both sides by 2,000. Now, 2 really important things that I want to point out. Number 1 is when I added all my equations together, I got the total mass of my system times my acceleration. That should always happen. You should always end up with the total mass of your system times the acceleration. And that makes sense because all 3 of those masses together are being accelerated. So the mass, when you combine them, should be the total mass. The second thing that happens is the forces between the objects, okay, end up canceling out. And that also makes sense. Those forces between object 1 and 2 and object 2 and 3 don't ultimately cause the system to accelerate. So they shouldn't be in our final equation. All that we're going to have is that overall force acting on the system, which in this case was just the pulling force of 8,000. It won't always simplify to a single force like it did here. Sometimes you will have multiple forces. This is a slightly simpler example, but it always should be forces that are kind of outside of our objects, not forces that are holding our system together. Once we have that acceleration, which is the answer to part A, we can now go back and think about the force that the third car exerts on the second car and the second car exerts on the first car. So for part B, I'm just going to take that acceleration that I just solved for and use my equation for the third car. Force of 2 on 3, that's that force I want to solve for, and that's just equal to 500 times my acceleration, which is 4. And so the force of 2 on 3 is going to be 2,000 newtons. And for part C, when I'm trying to find the force that 1 exerts on 2, I'm going to use the equation for car 2. So the force of 1 on 2 minus the force of 3 on 2 is equal to 800A. Force of 1 on 2 minus 2,000, because that's the force, that's the same as the force of 2 on 3, and that's going to be equal to 800 times 4. So I find that the force of 1 on 2 is equal to 5,200 newtons. We touched on this a little bit in the solution of the last problem, but another way we can kind of think about these problems is by thinking about the idea of a system. So a system is an object or group of objects, typically situations where the objects are touching or interacting with each other in some way. Otherwise, this idea of a system doesn't really help us. And we're going to treat all those objects as a single system and basically treat them as a single object. And so we're going to distinguish between the objects that make up our system and everything else, which we're going to call the environment. All right, so we're also going to talk about the system versus the environment. And this oftentimes is going to simplify our analysis when we think about it as a system rather than thinking about it as a group of 2 or 3 or however many objects. All of the laws of physics are going to apply to any system, okay, as long as we can isolate that system from the environment. So we're going to look at what that looks like in terms of forces with the sample problem. So before we jump into solving one of these with the systems method, let's just talk about a few tips. And I will say this before we get into it. The systems method definitely can be a little bit more difficult to set up, but once it is set up, I think it's easier to solve. So a few steps here for solving it with the systems method. We're going to select multiple objects to be our system, okay? And we're going to really then think about the objects in our system versus the objects outside of our system. And so when we go to solve these problems, we're going to basically treat our system like an object and solve this like a normal force problem. However, we're only going to consider forces that are outside the system, forces that come from objects in our environment as opposed to other objects within the system. Okay, and then we're going to do our F equals ma and solve from there. We do want to be careful with the direction of our acceleration. That's going to be an important aspect as always, but especially with our systems method. So I really think the best way of doing this is to look at an example problem. So I'm actually going to go back to the problem we just solved, and we're going to do it using the systems method. So the first thing I'm going to do is consider my system when I'm trying to find the acceleration of the cars, and I'm going to think about the forces that are acting on the system itself. So in this case, my system is going to be the 3 cars together. So we're going to treat that as one object. So what forces do we have acting on the system? Well, we have the normal force acting up on the cars from the track. We have the force of gravity from the earth, which is both those objects are in our environment outside of our system, so they're both valid. And we have this pulling force. And that's it. All those forces that acted between the objects here holding our system together, they are not forces that we're considering because we're treating all 3 objects as one object, as one system. And so now I can set up my F equals ma for this one. And I can say that my pulling force here is going to be equal to the mass, and the mass in this case is the mass of my system. So the mass of all 3 combined are 2,000 kilograms, right? The 500 plus 800 plus 700. And so I can say 8,000 equals 2,000a, so my acceleration is just 4 meters per second squared. As you can see, we got to that acceleration answer a lot quicker than we did before because we treated it as a system. For situation B, we want to know how much force is exerted on the 3rd car by the 2nd car. So once again, I'm going to think about all 3 of my cars. However, I'm going to select a slightly different system, and this maybe is a lack of system, but the system I'm going to select for this one is just the 3rd car. So the force is acting on the 3rd car. I have gravity in my normal, and then I have the force of 2 on 3, which is what we're looking for. So when I do my F equals ma, this is going to be just like the last one, force of 2 on 3, it's going to be equal to the mass, and now I'm only considering that 500, so I'm just using the mass of the 500 times my acceleration. And so I'm able to still find the force of 2 on 3. For my last question, how much force is exerted on the second car by the first car? I'm actually going to do something a little bit funky here, and I'm going to once again use my systems idea, but my system now is just going to be car 2 and 3. So they of course have gravity and the normal force acting on them. They also now have the force of 2 or of 1 on object 2. That is a force that's now outside my system because I'm only treating cars 2 and 3 as a part of my system. So I set up my F equals ma once again, and I have the force of 1 on 2 is equal to the mass of that system, so 500 and 800 together, or 1300, times the acceleration, which I know is 4, and so I find that the force of 1 on 2 is 5,200 newtons, which is the same thing as I got before. Okay, so this represents just a slightly different way of going about these problems. I think it is a powerful idea in certain situations, but it maybe doesn't always make your life easier, to be perfectly honest with you. So there will be some times when you solve it by looking at each object as an individual object, but other times it might be helpful to solve it as a system. One really important point that I think was emphasized nicely here is you can pick and choose what you want to be your system. You don't necessarily have to pick all of the objects in the problem if it doesn't benefit you. Sometimes you will pick all of them like we did for our first one. Other times we might just pick a single object or two objects and use the forces acting on them to find whatever we need to find.